going to focus on cyclohexane. It's a pretty common ring structure. We've said it's not planar, and from a planar shape it puckers, but we haven't said what configuration it does adopt. Well, the configuration is called chair. I wonder why that is. Perhaps it's because it's a chair shape. What do you know? Here we have somebody looking very comfortable sat down in a chair. Or is that a cyclohexane chair configuration? I really can't tell. Perhaps it's something you might buy from IKEA. It certainly isn't a very formal chair, but a chair nonetheless. How do we draw this configuration? Hold on. Why would you want to draw this configuration? Let's start there. Well, if you need to explain a spatial idea about a cyclohexane to a fellow chemist, unless you can draw the chair, they might have difficulty understanding you. Perhaps you're very gifted and you can pick up a pencil and the first time you freehand draw the chair, it looks perfect. If that's you, I'm very jealous. It's not most of us, and that's why I've provided some guidelines to drawing the chair. Hopefully you'll evolve to being able to draw the chair freehand, but this information is so that you can practice and get better at drawing it. Let's begin. We're going to draw two long dotted lines running parallel to each other. They're about half their length away from each other. The ends of the line are offset from each other by about a quarter of the full length of a line. Next, we want to introduce another shorter dotted line halfway along, a sixth the height and perpendicular to the longer dotted line. All those dotted line lengths are a scaffold for putting the full line lengths down that are going to represent our bonds. We're going to draw our full lines from the edge of the inverted T on the lower lines that are dotted to the top of the shorter dotted line and then down the other side of the longer dotted line. It should look something like a triangle now. Okay, that's one bottom section done. Let's do the same with the top section. Notice that the red lines of the bottom section and the top section are parallel, as well as the blue lines of the bottom and top sections also being parallel with each other. Finally, we're going to join up these two structures by drawing a full line from one end of the long dotted line down to the nearer end of the other long dotted line. We do this twice. Great. This is the basic structure sorted out. We can now remove the dotted lines. Here we have our carbons, but next we want to know where to place the substituents on the ring. We're going to put the substituents in here as hydrogens, but naturally they could be other atoms or functional groups. There is always one axial substituent on each carbon. The lines are either vertically straight up or down towards, in this case, a hydrogen. There's a clue as to which direction, up or down, within the ring. Within the ring you can see a V shape. If the V shape points down, you draw the line down. If the V shape points up, you draw the line up. Great. That's the axial substituents in place. Now we want to put our equatorial substituents in place. They are a little harder to draw than the axial substituents, but where the axial substituent is up, the equatorial substituent is down, and vice versa. They go at an angle, but you are going to find that they are parallel to not the nearest carbon-carbon bond line, but the next nearest carbon-carbon bond line along. Again, you have one equatorial substituent on each carbon, and each equatorial substituent's line or bond needs to be parallel with the appropriate carbon-carbon bond within the ring. This provides us with a close to perfectly drawn cyclohexane molecule. Let's bring all the equatorial substituents and axial substituents together and show them on the same cyclohexane. Still, for the equatorial substituents, the red hydrogen-carbon bond is parallel with the red carbon-carbon bond, the blue hydrogen-carbon bond is parallel with the blue carbon-carbon bond, and the green hydrogen-carbon bond is parallel with the green carbon-carbon bond. We do see another pattern here. On the left-hand side, we can superimpose the letter M using 2 of the equatorial hydrogens and 3 of the ring carbons. On the right-hand side, we can superimpose the letter W, again using 2 of the equatorial hydrogens and 3 of the ring carbons. Let's take a look at the cyclohexane down carbon 1 through the bond to carbon 2, and down carbon 5 through the bond to carbon 4. And imagine this in terms of a Newman projection. We can see that we have 6 axial hydrogens and 6 equatorial hydrogens. All the axial hydrogens are pretty obvious, and also 4 of the equatorial hydrogens are also pretty obvious. But the equatorial hydrogen on carbon 3 and the equatorial hydrogen on carbon 6 are kind of tough to realize they're equatorial from this viewpoint. But we have seen them from the other viewpoint, and we do know they're equatorial. Okay, so we have our chair conformation with its axial and equatorial substituents. Now this is conformationally mobile. It can what's called ring flip. So we can go from the conformation on the left to a new conformation on the right. It's still a chair conformation, but it's not the same chair conformation. Let's see if we can identify what has changed here. Well, we can see what are axial substituents and we can see what are equatorial substituents. And I'm going to focus on the axial substituent at carbon 1 on the left conformation. How does it change as we change through ring flipping to the right conformation? Well, it becomes equatorial. So an axial substituent as it ring flips become equatorial, and an equatorial substituent as it ring flips becomes axial. And you can see that's true for any carbon on this ring. Is there something here that is common to the left-hand side conformation and the right-hand side conformation? Well, there is, but we can't think of axial and equatorial. Clearly, they're changing. I want to think in terms of up and down. How do we work that out? Well, let's draw a dotted line horizontally through each carbon. If the substituent, either axial or equatorial, is above this line, let's call it up. And if it's below the line, we're going to call that down. And this is going to be true for any carbon you look at. But to start with, I want to focus on carbon 5 and the substituent that is up. Okay, what happens when we ring flip and go to the right-hand conformation? Well, that substituent stays up. Is there another example to spot? Okay, well, let's pick carbon 3. The substituent there I want to focus on is going down. As we ring flip to the right conformation, it remains down. And so it doesn't matter whether you have one form of the chair on the left or the other form of the chair on the right. The same substituent will stay down or stay up as you ring flip.